This is part 2 of section 4.5. I want to solve this equation. Skeletons were found at a construction site in San Francisco in 1989. The skeletons contained 88% of the expected amount of carbon-14 found in a living person. To the nearest whole number, how old were the skeletons in 1989? One of the things I notice is that they were found in 89 and they're asking how old they were in 89. That's good because it means I'm not going to have to make an adjustment at the end to say how old they were in a different year. So basically, if I can find the amount of time it took, then I have my answer. Okay. So what is going on here? The exponential decay model is right here. This is what we've used on a previous problem. What this is saying is the initial amount is how much carbon-14 is in a living person, and then carbon-14 starts to decay once the person dies. So, and it decays at a given amount. We know that. So basically what this is saying, the amount we have left in 1989 is 88% of A naught. Which is the same thing as 0.88 times A naught. So this is how much we have left. This is how much we started with. So let's just take this and plug it in right here. So 0.88 times A naught is equal to A naught times e to the negative 0.000121 t. Now notice what happens here. Remember, A naught is just a number. Maybe we're not given it, but we know it's a constant, so we could divide both sides by A naught. If you divide both sides by A naught, it goes away. Now, this is going to happen every single time you have one of these exponential decay models where you're given, when you have some sort of percentage or fraction of what you had left. So this is, if your value here requires that you use A naught to find it, it's going to cancel out. So what I really need to solve is 0.88 equal to e to the negative 0.000121 t. So this is an exponential equation, and we know how to solve these. I need to get this t out of the exponent, so that means I need to take a log of both sides, and I'm going to choose natural log because of the e value. So natural log of 0.88 is equal to, take the natural log of e to the negative 0.000121 t. And then you end up with natural log of 0.88 equal to, the natural log and the e undo each other, so it's equal to just the exponent. Okay. Now we should divide both sides by this decimal. So my time, before I even plug it in my calculator, I'm going to double check. I'm supposed to round to the nearest whole number. Okay. So my t value is equal to natural log of 0.88 divided by negative 0.000121. So let's type this in the calculator and see what we get. And I get about 1,056. So how old were these skeletons in 1989? They were 1,056 years old. Okay, so next problem. This is somewhat similar, but it is definitely more difficult. The half-life of lead is 22 years. So we know that if you have radioactive lead, it's going to take 22 years in order to decay. All right. How long will it take for a sample of the substance to decay to 80% of its original amount, round to 1 decimal place? So it's not going to reduce halfway, so I expect an answer that's going to be less than 22. But the thing is here, the big thing is that we're not given an equation to use. So we have to figure this out. And right here, this first sentence is enough for us to find a k value. Now what we have to remember is that our original is we have a is equal to a naught e to the kt. And if our k value is negative, then it's exponential decay, which is what I expect here. And if our k value is positive, it's exponential growth. The first thing we have to do is to find k. And right here, from the first sentence, we know that t is equal to 22. And we're talking about a half-life, which is how long it takes for our original amount to end up at half of this. So what I really need is 1/2 of a naught is going to equal a naught. This is the amount we have left after 22 years. So e to the 22k. Okay, now we know that our a naughts cancel out, and we can take natural log of both sides. Natural log of 1/2 is equal to natural log of e to the 22k. So this is natural log of 1/2 equal to 22k. So what is our k value? K is exactly natural log of 1/2 over 22. Okay, of course, you don't want to take this and rewrite your equation with this. Okay, so what I'm going to do is I'm going to figure out what this is, and I'm going to round to, let's say, 4 decimal places. It's sort of, if you look at right here at this k value, I'm not requiring as much precision as right here. Okay, so let's use a calculator and figure out what this is. Natural log of 1/2, and then divide that by 22. And so our k value, I expected it to be negative, and it is approximately, I should use approximately there, 0.0315. Okay, so I've used the fact that I knew its half-life to find out my k value. Now I'm going to write a more general equation right here. So my new and improved decay formula for lead is A equal to a naught e to the negative 0.0315 t. Now we want to use the rest of this. How long will it take for a sample of this substance to decay to 80% of its original amount? Now from here, it's basically the same as this problem. We found our formula to use. And right here it was 88%. Here it's going to be 80%. So this is 0.8 times a naught is equal to a naught e to the negative 0.0315 t. Our a naughts cancel. Use natural log. Natural log of 0.8 is equal to the natural log of e to the negative 0.0315 t. So natural log of 0.8 is equal to negative 0.0315 t. Now divide both sides by that. Okay, so my time, let's see what we get. It should be this. Now I expect time to be a positive number, and I see a negative in here. So I start to get a little bit nervous, and I'm going to watch that. I know my answer can't be negative, so I'll check for a mistake if I get something else. So natural log of 0.8, good. That gives me a negative number. So when I divide by a negative, I'll have a positive divided by negative 0.0. Okay, and I get 7.0839, so on. And now I look, we were asked to round to 1 decimal place. So it takes approximately 7.1 years to reduce to 80% of its original amount. This in some ways feels a lot like variation problems.